All right, welcome back, guys. And for the last problem that we're going to do for this, this unit of uniform circular motion, we're going to be tackling another banked curve problem. And the reason why this is a very good problem is because it's not only going to talk about uniform circular motion, but it's also going to have to use centripetal force, which we talked about earlier, as well as Newton's second law. And Newton's second law, we're never going to really leave that problem. And whenever you look at FRQs on AP Physics, at least a third of the problems that you're going to do is going to involve some form of Newton's second law. So if you haven't grasped that, if that unit just kind of slid by you and you didn't really pay attention, didn't really understand it, go back to that unit and make sure you understand Newton's second law and force very well before we start moving on. And as we move on through the year, that chapter and that unit is going to be expounded upon, is going to be utilized throughout the year even more. So this question says, a train traveling at a constant speed rounds a curve of radius 235 meters. A lamp suspended from the ceiling swings out at an angle of 17.5 degrees throughout the curve. What is the speed of the train? Now, this question is kind of formulated a little bit strangely, but we have to just understand what they're kind of trying to tell us. That 17.5 degree angle of the lamp within the train is really the angle of the curve itself, which makes sense because the angle that the lamp is going to be suspended from the ceiling is going to be the same as the angle of the curve. If the angle of the curve was 20 degrees, the lamp itself would also be at a 20-degree curve because it is attached to the train and the train is on that curve. If the curve was a 10-degree at a 10-degree angle, and then that lamp suspended from the ceiling would also have a 10-degree angle throughout the curve. So all they are trying to tell us here is that our curve angle, our bank curve angle, is 17.5 degrees. And this is going to be very helpful for us to later on throughout the problem. And here I have drawn the bank curve already. It's very similar to an inclined plane. However, we can draw it like an inclined plane, but we have to have the understanding within our head that this represents some sort of uniform circular motion. So we're turning in a complete circle. So we're going to have some sort of centripetal force and a centripetal acceleration towards the center. To start off with these banked curves, we're going to have our normal force normal, which is perpendicular always to the plane. So right here is our plane on which the train is on, our banked curve, and our force normal is perpendicular. As well, we're going to have force gravity, which is always acting towards straight down because force gravity goes towards the center of the Earth. And now, always whenever we start these problems, like we did in chapter 4, we want to get the x and y components of each of the variables given. And as we can tell here, force normal is neither in the x nor in the y. It's kind of just perpendicular to our bank curve. So we can draw its x and y components. However, we need to find out what that theta is. So we can just use some basic geometry and trigonometry. If this is theta, that's 90 degrees, then this has to be 90 minus theta because the entire triangle, the angles within the triangle have to add up to 180. So 180 minus 90, that's 90. So this has to be 90 minus theta because 90 minus theta plus theta is 90, and then 90 plus 90 equals 180. So this would be 90 minus theta. And to kind of just show you guys what I mean here, 180 is a sum. So that would include the 90-degree angle. That would include the theta here. And we'll just call this x, right? So x would then be subtract over the 90, and subtract over the theta minus theta. So this is just 90 minus theta. And then here, since this is a parallel line to the line here, this smaller triangle and this bigger triangle in its entirety are similar triangles, meaning that the angles are all the same, relatively speaking, in terms of where they are positioned. So since this is the same angle as this is also 90 minus theta. Now we can continue on and figure out that since this entire thing is a 90-degree angle, this entire triangle that I just formed, 90 degrees would be equal to our x value here, x plus 90 minus theta. So if we just do some math, we subtract over the 90, so we get x minus theta equals 0, and then x equals theta. So if that's theta through vertical angles, we know that that is theta as well. So now we can figure out what our x and y components are by using the same things, the same methods that we did in chapter 4 or in the chapter over Newton's law. And we can figure out that this would be Fn sine of theta, and this would be Fn cosine of theta, because that would be opposite over hypotenuse, sine, and adjacent over hypotenuse. So now that we have found our x and y coordinates of all the given variables, now we can kind of start working out this problem a little bit more. Well, we have to notice, though, that since this is a bent curve and since this uniform circular motion, we're going to have some sort of force radial. Remember, the acceleration, centripetal acceleration, is always pointing towards the center of the circle. So if the acceleration is pointing towards the center of the circle, the summation of the forces is also pointing towards the center of the circle. It's kind of like the idea of pushing a cart. The direction that you push the cart in, or the direction you push any object in, the force, the direction that it's going to accelerate is in the same direction as the direction of the force you apply to that object. So now we want to give our summation in the x and our summation in the y. So our summation and the forces in the x is going to be equal to our Fn sine of theta, and that's positive because it's acting in the same direction as our centripetal acceleration. It's back to our basic example. If you are pushing an object in the same direction it's accelerating, your force is adding to that acceleration. It's accelerating it. If you add a force in the opposite direction that something is moving, so for example, say there's a car slowly moving down in neutral and you're pushing against it, well, you're decelerating it with that force, so the force is negative. So this is a positive force, and there's no other x force. The only other force is force gravity, and that acts straight down, so that's in the y direction. So Fn sine theta would be equal to m/ar. M being the mass, ar being the centripetal acceleration or radial acceleration. And the reason for that is because it's moving straight towards the center of the circle, or the acceleration, not the object itself, is accelerating towards the center of the circle. And we talked about that earlier within the playlist. Centripetal acceleration means radial acceleration, which means acceleration towards the center of the circle. And we've talked about that radial acceleration is v squared over r, so that is going to be equal to mv squared over r. So then we can simplify that by saying Fn sine of theta is equal to mv squared over r. Now we want to work in our y direction. And now we actually have two forces. Have summation of the forces in the y is equal to now Fn cosine of theta, right, since it's moving in the y direction, minus mg is equal to ma. And no longer is it mv squared over r, because no longer is the net acceleration pointing towards the center of the circle. That's the x component. The y component has nothing to do with our radial acceleration. And in this case, since obviously our train is along the bent curve, it's not flying upwards or downwards, the acceleration is 0. It's not going up or down, it's staying level along the plane. So then we can simplify that by saying Fn cosine of theta equals mg. Now, to solve this is kind of like our inclined plane. We know that the force normal is constant throughout. This is a force normal, this vector right here. We just took the x and y components of it. The x and y components differ, obviously, unless it was at a 45-degree angle, because then cosine theta and sine theta would both be the same, that being root 2 over 2. But since theta is not 45 degrees, they're different. But the original vector Fn stays Fn. We didn't touch it. So what we can do is set both of these equations equal to Fn, and since Fn is constant, then we can set those equations equal to each other. That being said, now we can simplify this by saying Fn is equal to mv squared over r sine of theta. And we can do the same over here. Fn equals mg over cosine of theta. Now these two equations we can set equal to each other because they're both equal to Fn. So we can now say that mv squared over r sine of theta is equal to mg over cosine theta. Then we can divide out an m. We can multiply over a sine of theta, so get v squared over r equals g sine of theta over cosine theta. G sine of theta over cosine theta is the same as g tangent of theta. And then we can continue simplifying and we get v equals root rg tan of theta. And that's it. What we did was we took Newton's second law. We had to first draw our force diagrams. Always draw force diagrams. Then we use our idea of centripetal acceleration. We recognize that our x forces, the summation of it would have an acceleration towards the center of the circle, meaning that it would be a centripetal acceleration, meaning instead of ma, it would be mv squared over r. We notice that Fn is constant throughout, not the x and y components, the original Fn vector. And by setting those two equal to each other, we were able to derive an equation that would solve for v. And this is why I love this problem so much. We had to do, I think, two different chapters, all sections, all ideas, all concepts in order to get this one answer. And then we get v equals root r is 235 meters. G is 9.80 meters per second squared. And then times tangent of 17.5 degrees. And that should give you an answer of 20... Oh, wait. That was a different problem. I have to actually plug it in. 235 times 9.80 times tangent of 17.5, square root that, and we get an answer of 26.96 meters per second. And then obviously you could round that to 3 sig figs, which would not be that difficult. And there you have it.